The most important hardware behind today's AI revolution was not originally designed for artificial intelligence. It was designed to draw video game graphics. That hardware is the GPU. Right now, AI companies are spending billions of dollars building data centers filled with GPUs. Powerful graphics cards sell out almost instantly, and access to advanced GPU clusters has become one of the biggest advantages an AI company can have. But why? Why is a graphics processor better at training AI than the CPU, the processor that actually runs the computer? The answer is not that GPUs are smarter than CPUs. They are built to work in a completely different way. A CPU is like a small team of highly skilled engineers. It usually contains a limited number of powerful cores, and each core is excellent at handling complicated instructions, making decisions, switching between tasks, and responding to unpredictable events. That is exactly what a general-purpose computer needs. When I open a browser, move a file, launch an application, type on a keyboard, or connect to the internet, the CPU coordinates everything. It may need to stop one task, prioritize another, check multiple conditions, and decide what happens next. The CPU is built for flexibility. A GPU is built for scale. Instead of having a small number of extremely powerful cores, a GPU contains hundreds or thousands of smaller processing units. Each one is less flexible than a CPU core, but they can all work at the same time. So I like to describe the difference this way. A CPU is a small group of experts, while a GPU is an enormous army of workers. And AI training needs the army. Training a neural network involves an unbelievable amount of mathematics, but most of that mathematics is surprisingly repetitive. An AI model contains millions or billions of parameters. These parameters are basically numbers that control how information moves through the model. During training, data enters the network, passes through many layers, produces an answer, and is compared with the correct result. The system calculates the error and adjusts the parameters slightly. Then it does the same thing again, and again, and again, sometimes trillions of times. At the center of this process are matrix operations. A matrix is essentially a large grid of numbers. AI training constantly multiplies these grids, adds values together, and applies simple mathematical functions to the results. One calculation may be simple. The problem is that the model needs to perform billions or even trillions of them. A CPU can do matrix multiplication, but it only has a relatively small number of cores available. It processes the work in limited groups. A GPU can split the same matrix into thousands of smaller pieces and calculate many of them simultaneously. This is parallel computing, and it is the main reason GPUs are so effective for AI. Imagine I give one person 10,000 simple math questions. That person may be incredibly intelligent, but they still need to answer the questions one after another. Now imagine I give those questions to 10,000 ordinary workers. Each worker solves only one question, but they all start at the same time. The second group finishes much faster. That is basically what happens inside a GPU. And this architecture originally existed because computer graphics had exactly the same problem. When a computer renders a game, it needs to calculate the position, color, lighting, texture, and shadows of millions of pixels and geometric points. Many of those calculations are similar. More importantly, they can often be performed independently. The GPU does not need to finish calculating one pixel before starting the next one. It can process thousands of pixels together. Researchers eventually realized that neural networks had a very similar structure. Instead of applying the same calculation to millions of pixels, AI applies the same calculation to enormous collections of numbers. Different data, same basic computing pattern. That is how a piece of gaming hardware became the engine of modern artificial intelligence. But parallel processing is only part of the story. The second major advantage is memory bandwidth. AI training does not just calculate numbers. It constantly moves them. The system needs to load model parameters, read training data, store intermediate results, calculate gradients, and update the model. This creates a massive flow of information between memory and the processor. A processor may be extremely fast, but if data cannot reach it quickly enough, the processing units sit idle. Think of a huge factory with thousands of workers, but only one small delivery entrance. Even if the workers are fast, production stops whenever they run out of materials. GPUs are designed with extremely high memory bandwidth because graphics also require huge amounts of data to move quickly. Every frame in a modern game may involve textures, geometry, lighting information, and millions of pixel values. GPUs need to access all of that data continuously. The same design is perfect for AI. This is why GPU memory, often called VRAM, matters so much. During training, the GPU needs to store much more than the model's parameters. It may also hold activations, gradients, optimizer states, and batches of training examples. A model may appear to be a certain size when downloaded, but training it can require several times more memory. When the model is too large for one GPU, engineers have to divide it across multiple GPUs. Some GPUs process different groups of training data, others store different sections of the model. The devices constantly exchange information and synchronize their results. This allows companies to train models that would be impossible to run on a single machine. But it also creates a new problem: communication. The more GPUs we connect, the more time they may spend waiting for information from one another. At a certain scale, networking becomes almost as important as the processors themselves. That is why an AI data center is not simply a room filled with graphics cards. It also needs ultra-fast connections, specialized networking equipment, powerful cooling systems, enormous electrical capacity, and software that can coordinate thousands of devices. Modern GPUs also contain specialized units designed specifically for matrix mathematics. These units can perform huge numbers of multiplication and addition operations in a single step. Since neural networks rely heavily on exactly these operations, specialized matrix hardware can dramatically accelerate training. Another advantage is lower precision computing. Traditional software sometimes requires very precise numbers. AI models often do not. Neural networks can usually train successfully using number formats that contain fewer bits. The numbers become slightly less precise, but they use less memory and can be processed much faster. Smaller numbers mean the GPU can move more data, perform more operations, and fit larger models into memory. In many cases, the system mixes different precision levels. It uses lower precision for speed and higher precision where stability is important. This is known as mixed precision training, and it has become a standard technique for accelerating modern AI workloads. So does this mean the CPU is no longer important? Not at all. The CPU still runs the operating system, prepares training data, controls storage, manages network connections, and coordinates the overall training process. The GPU handles the enormous waves of parallel mathematics, while the CPU manages the workflow around them. I think of the CPU as the conductor and the GPU as the orchestra. The conductor controls the performance, but the orchestra produces the massive sound. And not every AI task needs a GPU, small machine, learning models, data processing pipelines, and programs with lots of complicated decision-making may run perfectly well on CPUs. GPUs perform best when a large problem can be divided into many similar pieces, if every calculation depends heavily on the result before it, or if the program constantly follows different logical paths. The GPU may lose much of its advantage. There is also an important difference between training and inference. Training means teaching the model. It requires repeated forward passes, error calculations, backpropagation, and parameter updates. This is extremely computationally expensive. Inference means using the finished model to generate an answer or make a prediction. Large AI services still use GPUs for inference because they need to serve thousands or millions of users, but smaller models can run on CPUs, smartphones, laptops, and dedicated AI chips. The GPU is not automatically the best processor for every situation. It is simply extremely well matched to the mathematics of deep learning. Software also played a huge role in its success. Powerful hardware is useless if developers cannot easily program it. Over time, companies and researchers created programming platforms, optimized libraries, and machine learning frameworks that automatically convert AI operations into GPU instructions. Today, when I build a neural network, I usually do not need to control thousands of GPU cores manually. The framework handles most of that work. This created a powerful cycle. More researchers used GPUs, so more AI software was optimized for GPUs. Better software attracted more developers, and more demand encouraged companies to build even faster hardware. That hardware and software ecosystem is one of the biggest reasons GPUs continue to dominate AI training. Other processors are now entering the market. We have TPUs, NPUs, custom AI accelerators, and chips designed specifically for certain neural network workloads. Some of them may be more efficient than traditional GPUs in specific situations, but GPUs remain incredibly valuable because they combine massive parallel performance with flexibility and a mature software ecosystem. So when someone says a GPU is faster than a CPU, that statement is incomplete. A GPU is not faster at everything. A CPU is better at complicated logic, unpredictable instructions, and rapidly switching between unrelated tasks. A GPU is better when the same mathematical operation needs to be repeated across an enormous amount of data. And that is exactly what AI training is. Training artificial intelligence is not like asking one genius to solve one extremely difficult problem. It is like asking thousands of workers to perform trillions of small calculations at the same time. The CPU gives us a few brilliant experts. The GPU gives us the workforce. And that massive parallel workforce is one of the main reasons today's AI models can exist at all.